When a modern AI solves a hard problem, it writes out a long chain of thought, sometimes hundreds of sentences. But here's a question almost nobody can answer. Out of all those sentences, which ones actually mattered? Which were the pivotal moments that steered the whole solution, and which were just filler the model could have skipped? This paper introduces a beautiful idea. Inside a long reasoning trace, a few special sentences carry outsized influence. The authors call them thought anchors, and they build 3 independent methods to find them, 3 completely different lenses that, remarkably, all point to the same sentences. First, why sentences? Interpretability usually studies single tokens or a whole forward pass, but reasoning unfolds over thousands of tokens across many steps. The authors argue the sentence is the sweet spot, big enough to be a coherent reasoning step, small enough to pin down precisely. And here's their central claim. Not all reasoning steps are equal. A few sentences, usually planning or uncertainty management moments, act like anchors. They set the plan, catch a mistake, or change direction, and everything downstream pivots around them. Find those, and you understand the skeleton of the whole reasoning trace. Before the methods, here's the payoff. 3 separate techniques, black box resampling, attention analysis, and causal masking, all converge on the same special sentences. Planning and uncertainty, steps consistently dominate. And specialized attention heads physically point back to these anchors. 3 lenses, 1 consistent picture. Let's see how each works. Now the heart of the paper. How do you measure whether a single sentence truly mattered? The challenge is that you can't just read the text and decide. You need a principled, causal test. The authors build 3. Let's go through each one carefully. Start with the old way to see why it's not enough. Prior work measured importance by interrupting the model at each sentence and forcing it to answer right there. Problem: a sentence might be essential but always appear late, like a final arithmetic step. Forcing an early answer makes everything before it look useless, hiding the real planning sentences. Method 1, black box resampling. The idea is a counterfactual. For a given sentence, run the reasoning forward 100 times with that sentence included and 100 times without it. If the distribution of final answers shifts a lot when the sentence is present, that sentence had real causal influence. If nothing changes, it didn't matter. There's a subtle refinement here that's really clever. When you resample a sentence, sometimes the replacement is basically the same sentence reworded, which tells you nothing. So they only count cases where the replacement is genuinely different in meaning, measured by embedding similarity. That gives a clean signal they call counterfactual importance. A quick case study makes it vivid. The model is converting a base 16 number to binary. For a stretch of sentences, expected accuracy drifts downward. The model is heading toward a wrong answer, 20 bits. Then one sentence, sentence 13, where it decides to convert to decimal instead, causes accuracy to jump sharply. That single sentence is the anchor that rescues the solution. To test this systematically, they label every sentence by function: problem setup, plan generation, fact retrieval, active computation, uncertainty management, and so on. Then they ask which categories carry the most counterfactual importance. The answer is striking. Planning and uncertainty management sentences dominate, while raw computation matters far less. Method 2 flips from behavior to mechanism. If a sentence is an anchor, maybe later sentences literally pay attention to it. The authors hunt for what they call receiver heads, attention heads that sharply focus on a few specific past sentences instead of spreading attention evenly. They measure this focus with kurtosis, a statistic for how spiky a distribution is. And these receiver heads are real and consistent, not noise. Split the problems in half, and a head's focusing behavior in one half strongly predicts the other, a correlation of 0.84. Different receiver heads even point at the same sentences. Ablate them, and accuracy drops more than removing random heads. They're doing real work. And here's the first beautiful convergence. The sentences that receiver heads focus on are the same types that resampling flagged as important: planning and uncertainty management. 2 completely different methods, one from behavior, one from internal attention, agree on which sentences are the anchors. Method 3 maps the connections between sentences. For each pair, they suppress all attention to an earlier sentence and measure how much a later sentence's predictions change, using KL divergence on the token logits. Big change means a strong causal link. Do this for every pair, and you get a causal graph of the entire reasoning trace. And this one is practical. Suppressing attention is almost the same as deleting a sentence, but it only needs the model's output logits, which many APIs expose. That makes it roughly 100 times cheaper than full resampling, so they can scale it to thousands of reasoning traces. So that's the toolkit: resampling, receiver heads, and causal masking. We've seen the first two agree. Now, what does the causal graph reveal when you zoom out to thousands of problems? It turns out the shape of the graph tells you something deep about reasoning itself. The key insight: the distance of causal links tracks how a model reasons. When sentences mostly connect to their immediate neighbors, close-range links, the reasoning is tightly structured, each step cleanly causing the next. When sentences connect across long distances, the model is uncertain, jumping around and backtracking. And this structure predicts real things. Problems the model solves accurately tend to have strong close-range links and weak long-range ones, tight reasoning. Math and physics, where the model excels, show exactly this firmly structured pattern. Fuzzier domains like history rely on more scattered, long-range reasoning. The graph's geometry mirrors the nature of the task. There's a deeper implication, too. Some researchers worry that a model's written chain of thought is unfaithful, just a story disconnected from the real computation. But here, the sentences that say they're planning or expressing doubt are exactly the ones that mechanically matter most. The text says lines up with what the computation does. The reasoning text is meaningful. Let's pull it together. Thought anchors gives us a principled way to decompose reasoning into sentence-level steps, and to find the few that truly steer the outcome. 3 independent methods: behavioral resampling, attention receiver heads, and causal masking, all converge on the same planning and uncertainty sentences. That convergence is the paper's strongest evidence. Why care? Because as we hand bigger decisions to reasoning models, we need to debug them, audit them, and catch failures. If you can pinpoint the exact sentence where a solution went right or wrong, you can understand and fix reasoning far more precisely than by reading a wall of text. The authors even released an open tool, thoughtanchors.com, to visualize it. The authors are upfront that this is early work. Sampling 100 times per sentence is expensive. Attention suppression pushes the model slightly out of distribution. And receiver head scores are partly confounded by a sentence's position. Honest caveats, but the surprising agreement across 3 very different methods is what makes the core idea convincing. So here's the one-line takeaway. A long chain of reasoning isn't a flat list of equal steps. It's built around a handful of pivotal sentences, the thought anchors, where plans are set and doubts are resolved. And we can now find them 3 different ways that all agree. It's a real step toward actually understanding how AI thinks. Thanks for watching.